Do you want to learn how to create animations like this in real time without writing a single line of code? But have you never ever written a program designed for running on a graphics card? Well, then you are at the right place. These beautiful animations are just a few mouse clicks away. We can almost effortlessly use the powerful Blender render engine to create these animations as shader images. All what has to be done is connecting a few shader nodes. Let's dive right into it. The default cube is removed and replaced by a plane. Hit 7 on a numpad to go into the bird's eye perspective. We also need the shader editor and we can remove the timeline. The plane is scaled appropriately. Since most of the action goes on in the shader editor, it is shown in full screen. The transformations on the plane in the 3D viewport are shown as a backdrop image in the lower right corner. A new material is added to the plane. The default nodes, the principled BSDF node and the material output node, are automatically generated. We decrease the roughness of the plane material to get some nice reflections on the surface. The plane is considered to be a two-dimensional coordinate system or a part of the complex plane. In the language of shaders, the plane is equipped with UV coordinates, which range from 0 to 1 in each direction. The first node that we add will rescale these UV coordinates to our demands. We need a 2.6 times larger coordinate system which runs from -2.1 to 0.5 in x direction and from -1.3 to 1.3 in the y direction. The x and y coordinates of each point on the plane are treated as a complex variable. Let's first of all visualize the phase of these complex numbers. The phase is computed with the arctangent of y over x. The function arctan2 returns values between -pi and pi. We need to map them between 0 and 1 to display them as u-color values. This can be achieved by scaling with 1 over 2 pi and shifting by 1/2. The mapped phase values are piped into the U value of a color node and its color values are linked to the base color of the principled BSDF node. Immediately the complex phase plot for the plane appears. You can spot the origin and the phases circling once around it. The conversion of phases to colors is packaged as a group node and labeled with phase to color. Now everything is set up to actually compute the Mandelbrot set. It is defined by the following iterative function for a complex variable set. The Mandelbrot set consists of all those complex points z for which the iteration stays finite. The real and imaginary part of z are labeled by x and y. Similarly, the real and the imaginary part of z are labeled by z sub x and z sub y. The iteration can then be restated in terms of the real and imaginary parts. Now all variables are real numbers and the shader nodes can operate on them. For the real part, the square of the y value is subtracted from the square of the x value and shifted by the real part of z, which is equal to the real part of z for the first iteration. Similarly, the imaginary part is computed by the product of x and y, scaled by 2 and shifted by the imaginary part of z. Finally, the real and imaginary part are combined to a new complex number, which is piped into the color function. For each point of the plane, the iteration is performed parallelly on the GPU, and the result is shown immediately on the material shade of the plane. The computation of the iteration is packaged as a second group node, the inputs and outputs are labeled accordingly, and the entire node is called iteration. The iteration node can be applied an arbitrary number of times repeatedly. Now it should be clear why we have to distinguish the two inputs. The result of the first iteration node is piped into the z value of the second iteration. The z value, however, is given by the point at the plane the iteration is performed at and is directly obtained from the rescaled UV coordinates. You can nicely see in real time how each iteration changes the shader of the plane. If no z value is attached, the action of the node is a simple squaring operation. The phase winding number at each 0 just doubles. The non-trivial z value lifts the degeneracy of the zeros and causes a doubling of zeros for each iteration, and the locations of the zeros are closely related to the shape of the Mandelbrot set, which is materializing after a few iterations. Outside of the Mandelbrot set, the iteration quickly yields overflows, which are interpreted as bright colors in the phase to color node. This is a bit annoying but also quickly fixable. We only have to check the absolute value of the complex number. If it is larger than 2, it definitely lies outside of the Mandelbrot set and the comparison yields 0. This 0 is used to darken the color at this pixel. In the Mandelbrot set computations, one usually keeps track of the number of iterations for each pixel. The number of iterations that are needed to see that a pixel does not belong to the Mandelbrot set is usually color-coded in the corresponding plots. Therefore, we add a similar set of nodes to the iteration group. When the absolute value of the incoming complex number is smaller than 2, the iteration counter is increased by 1. We use the unused z component of the vector to store the number of iterations. After the last iteration, the value of the iteration for each pixel is mapped between 0 and 1 by rescaling it with the total number of iterations. This value is used as a height displacement, and when it is plugged into the material output, it causes nice level lines of iterations. The outside of each line marks the set of all points where a fixed number of iterations has exceeded the value of 2. These boundaries narrow in on the boundary of the Mandelbrot set in the limit of infinite iterations. We can further use this information to change the colors accordingly. Everyone who has computed the Mandelbrot set before knows the efforts that have to be taken to perform this iteration across all the pixels of the plot or screen. Here the GPU performs the computation of every pixel in parallel and presents the result within fractions of a second. Shifting and rescaling of the plane during zooms and changes of camera position are all managed by the render engine. So these few nodes in the material shader open a window for fully interactive explorations of the Mandelbrot set. We give a hint for the possibilities of explorations. An empty cube is added to the scene. The camera is tracked to this empty. The focal length of the camera can be increased with an optical zoom and reveals more details on the fractal boundary of the Mandelbrot set. Right now it seems that there are featureless spots in the middle of the flowers. When the iteration value is rescaled, these colors circle in real time through the fractal. Now you can perform a little benchmark test of your GPU. We double the number of iterations one more time. Having a total of more than 100 iterations, the before featureless regions have enriched in beauty. There are now 2.6 times 10 to the 36 zeros inside the Mandelbrot set, defining the fractal structure at these levels of zoom. So far everything was performed on the level of shaders on the GPU. But since we've come so far, let's create one of my favorite representations of the Mandelbrot set. The plane is endowed with a few loop cuts that create a mesh of 100 little squares. This mesh is refined by a subdivision modifier. We turn on the experimental settings of Blender, and then we can choose the option of adaptive subdivision. Finally, the displacement information is turned from bumps into actual displacements. It takes a second or two, but then the cycle renderer converts the information about the number of iterations into actual heights and a nice three-dimensional Mandelbrot set appears. A second video where a few more technical details of the Mandelbrot set will be discussed is in preparation. If you are, for instance, interested in why the threshold for the iteration can be chosen to be 2, or how the shown level curves can be computed analytically, stay tuned for the next video. See you soon, goodbye.